Very good.
Hello. Sir, are you there?
Okay, I'm
Sir, are you there?
Okay, I'm here. I'm here. Let's start it. Hello. Hello. Am I audible?
Yes, sir. Yes. Yes, sir. Audible.
Hello.
Good evening, everyone. I welcome everyone on our sixth session of ATAL FDP on fundamental of thin film preparation and characterization technique on the behalf of Department of Physics, Tripura University. Today's lecture will be delivered by Professor Bhattacharjee, Department of Physics, Tripura University. Title of his topic, Basic Introduction to the Principle and Working of the UV Vis absorption spectroscopy, fluorescence spectroscopy, and Bristol angle microscopy. Professor Bhattacharjee is a professor of Physics, Tripura Department of Physics, Tripura University, India. He joined the department in 1999. His major field of interest are the preparation and characterization of ultra-thin film by Langmuir-Blodgett self-assembled techniques. He has more than 100 research publications in reputed international journals. He has several projects from DST, Government of India, CSR, Government of India. Already 9 research scholars were awarded PhD degree working under his supervision. So, and after this session, there will be an MCQ test. I request all of you to present till the end. Sir, you may now start, sir.
Okay. Very good evening to everybody. I am now sharing my presentation. Okay, and this is in PDF format. Actually, general convention is that to present in a PowerPoint presentation, but actually it's a lecture note, and therefore it is presented in this. And also I prepared the video lecture using these lecture notes, and therefore I am presenting it in PDF format. It's no problem, but the font is also in 16 point, therefore it can easily be viewed. And now this lecture on this topic is that this UV absorption and fluorescence spectroscopy. And also first of all, I thought to present also this Brewster angle microscopic in situ, of course, but time is very limited. actually to discuss in detail this absorption spectroscopy and fluorescence spectroscopy, it takes around 6-hour lecture period total. But I have to complete it up within 2 hours, and then it's really difficult to speak again about this BAM spectroscopy. Okay, and now first thing is that this characterization technique, and you know that these characterization techniques, these are extremely important in every science and technology. And in what we are doing in this department, I and also Arthur, and we are doing in this material science. In a broad sense, it's a material science, thin film, and nano particles and nanoscience also, and also different applications in this thin film. And in this material science, and not only material science, in science and technology, these characterizations is very much important. And because when you characterize any sample, first of all, what you have to do is that you have to prepare a suitable material, or you have to design a suitable sample for some particular use, and then you have to characterize it, whether the sample is suitable for this particular application or not, that you have to characterize it. And for this characterization, there are a large number of characterizing instruments depending on some particular use. And for example, you see that purity level checkups. Whenever, say in any organic or inorganic chemistry or polymeric chemistry, or even in nanoparticles also, when you prepare some materials or compounds for some particular use, and then first of all, what you have to do that you have to check the purity level of the sample. And that purity level checking, there are various techniques. I am just mentioning here some of the techniques. One is that melting point testing, that is a pure sample has a fixed melting point if it is in crystalline nature, but for amorphous there may be some range of this melting point. And that another for liquid material, that viscosity, surface tension, and also that NMR characterization, IR, FTIR, the purity level can also be checked using this IR and FTIR, and that UV Vis absorption, fluorescence spectroscopy, atomic mass absorption spectroscopy, and also there are several other spectroscopic techniques. And you see that in the master degree courses in physics, chemistry, and different biological science and engineering subjects in India, they studied a lot of things, lot of theory and some practicals also, of course. But the most important thing is that the student must be very much acquainted with the different types of modern characterization techniques or characterization instruments. At least every student must know the basic principle of several important instruments or equipments. And these important instruments and equipments are those important instruments and equipments, and it is that UV Vis absorption and fluorescence spectrophotometer and their principles. And now you see that in this research work, when you want to increase the purity level of a sample or material, and that purity level, it can be increased by HPLC, GC, LC, and also you see that crystallization method is another important technique for the purification of a chemical substance. Maybe that many of you know how to purify to the utmost level, say 4N, 5N level, that is 99.9999 and so on. Up to this level, there are also some other sophisticated techniques by this technique. You can purify your samples also. And for liquid sample also, that another important method is the distillation technique. The vacuum distillation, ordinary distillation, fractional distillations, and these are methods. These methods are used for purification of the sample. And then for some particular uses, you may use this optical characterization techniques. That is a spectroscopic characterization technique, that is FTIR, Fourier transform infrared spectroscopy, UV Vis absorption, fluorescence, ESR. Also, you see the lifetime measurement, lifetime. This is also another important spectroscopic techniques, a lifetime, picosecond lifetime, or say nanosecond lifetime measurement. These are important things. And then NMR, Raman spectroscopy, etc. And this electrical characterization technique for industrial applications of these various electronic equipments, electrical equipment, this electrical characterization technique is extremely important. That is the IV characteristics, current versus voltage characteristics. And even you see for photodiode, for solar cell, for light emitting diode, LED, and different types of FET, MOSFET, transistor, for development of any or investigation of any of these types of equipments, optoelectronics equipments, this IV electronics and optoelectronics equipment, of course, this IV characteristics is important. And here, when we just fabricate the film, we also use this IV characteristics techniques for to check whether that particular sample can be used for some device fabrication, like this memory switching devices, ROM, RAM, extra devices, whether it can be applied. And then that another thing is that this electroluminescence spectroscopic technique, and here this electroluminescence spectroscopic technique is same as that of the photoluminescence or fluorescence spectrophotometer. Only thing is that what you have to do is that you have to say you just coated some film here, and on this film, generally this film is coated on some I2O background. This is some I2O, and then this I2O plates. Some films are deposited, and here some vacuum deposition, some metal, say aluminium, gold, etc. deposited, and then it is connected. And some voltage is given here, some current moves, current flows through it, and then it luminesces, or it fluoresces some light in the visible range. And this can be measured by this fluorescence spectroscopy. And that is this electroluminescence spectroscopy is nothing but some fluorescence spectroscopy where some film can be attached and some electrical signal or electrical voltage can be applied on this film so that some light can emit. And this is the electroluminescence spectroscopy, and this is an important technique for LED application, light emitting diode application. And this electrical characteristics are required for checking the suitability of a material in various electronic application in the industry and in solid state electronics. And also you see for different types of sensor techniques, so blood sugar sensor, say alcohol sensor, this mainly these IV characterization techniques are used. And here you see that for designing this sensor, that is blood sugar, alcohol sensor, methane gas sensor, this IV characterizations is important. And here what you have to do that is when you just put some blood, and here you see that some thin film which is inserted in some instrument where this current is recorded, and this current is converted or calibrated for this blood sugar level sensor. And when some blood drop is put here, you see, then this blood drop it reacts, and the sugar presence in this blood drop, it reacts to the sample presence on this thin film, and as a result the conductivity increases, and this current increase, that is the current increases, and this current increases is calibrated in terms of the sugar level, and that will measure the sugar level. And this alcohol sensor also recently we also prepare some colorimetric alcohol sensor. That is when some alcohol vapor, you just drink some alcohol and puff this alcohol vapor on a thin film, its color changes from bluish color to red color and so on. And just by observing the change in color, you can say that whether a man is drunk or not. But in conventional alcohol sensor also, this colorimetric color, this IV characteristic sensor is used. That is a thin film is used, and when some drunk person just puff on this thin film, the alcohol in this vapor, it reacts to these materials on this thin film, and as a result, the conductivity increases, and then police can detect whether this person just takes some alcohol or not. And also that another important thing is that pregnancy kit sensor. It's a colorimetric sensor that is just by observing the change in color, we can confirm that whether an woman is pregnant or not. And these are the very important sensors, and also that methane gas sensors, these are used in some mines and others. And also that IV characterization studies, and it is also important for the fabrication of semiconductor and conductor devices like FET, MOSFET, op-amp, etc. And Then characterization, structural characterization, that is X-ray, CT scan, ultrasonography, same, FIM, BAM, also you see BAM, AFM, TEM. And in situ, this Brewster angle microscopy, we have this Brewster angle microscopy in situ with this Langmuir-Blodgett. It is in situ with this Langmuir-Blodgett instrument. LB instrument in situ. That is during the fabrication or preparation of these films. It can be directly observed by these BAM images. And how this film is developed gradually with the passage of time, how the film is developed, or how the orientation of different domain structure is formed, that can be directly visualized by this Brewster angle microscopic study. Now, the instruments and characterization techniques used for this atomic absorption, FTIR and others. And now spectroscopy. What is spectroscopy? This is a basic definition. That is, it is a branch of science that deals with the study of interaction of electromagnetic radiation with the matter. That is a study of the interaction of electromagnetic radiation with the matter. That is the various samples, materials we use, or nanoparticles we use. And these various spectroscopic techniques are used for the characterization materials to check their suitability for various technical applications. Now, what is spectrum? And you see, the spectrum is a graph in the spectroscopy. That is, that graph may be of the following type. That is the intensity versus frequency. It is used in IR spectroscopy or FTIR spectroscopy, intensity versus wavelength, and it is used in UV Vis absorption and fluorescence spectroscopy, intensity versus wave number, nu bar, it is used in Raman spectroscopy. And mainly these three types of graphs are drawn, and that is called the spectrum. And in plural, it is spectra. And now electromagnetic radiation, that electromagnetic radiation consists of the discrete packages which are called phonon, and a phonon consists of oscillating electric field and oscillating magnetic field, and which are perpendicular to each other. All of you know this thing, but the intensity of this electric field is 3 into 10 to the power 8. That is E by B ratio intensity. That is C. That is 3 into 10 to the power 8 times. That is this electric field intensity. That is 3 into 10 to the power 8 times that of the magnetic field. And therefore, in general, when an electromagnetic radiation is incident on the matter and these atoms and molecules of the matters interact with this oscillating electric field and not with the actually they also interact with the magnetic field, but this magnetic field interaction is negligibly small, and therefore we concern only the interaction of the oscillating electric field with the matter. Okay, and these are the different EM radiation in terms of the frequency or wavelength. Wavelength for gamma radiation, these are the very, very small wavelength, then X-ray, then UV. Wavelength gradually increases. And frequency, these are this gamma ray frequency is the largest frequency. But before that, also this cosmic ray also. Cosmic ray. These are the strongest frequency, largest frequency, and then gamma ray, X-ray. Gradually the frequency decreases, UV visible. And this UV to visible range 200 to say around 700, but actually it's very difficult to 700 nanometer in terms of wavelength. And you see in this visible range, that is, you say this around 400 or 420, but it's very difficult to see 420. Actually, you may see it 450 or 660 nanometer to 700 nanometer maximum. 700 nanometer or 650 nanometer, it's a red. Okay, and this is a small range. It is visible light, and also there is UV light from 200 nanometer to around 400 nanometer, and then it is IR. IR means this heat energy. IR, that is the frequency of this heat of thermal energy. Heat energy of thermal energy, and then also we have microwave and radio wave for telecommunication. For telecommunication purpose, we use this microwave and radio wave. And these properties of the spectroscopy, the principal is based on the measurement of the spectrum of a sample. And you also note this thing that generally this UV Vis absorption, and fluorescence spectroscopy, it is deal to this UV and visible range. And therefore, this principle of spectroscopy, this principle is based on the measurement of the spectrum of a sample containing atoms or molecules. Now, absorption spectroscopy, and this is an analytical technique which concerns with the measurement of absorption of electromagnetic radiation with the matter. For example, UV Vis absorption spectroscopy, UV range 185 to 400 nanometer, and the visible range 400 to 800 or 420 to 700 nanometer. IR range also. That's and fluorescence spectroscopy, and it is an analytical technique in which emission of a particle emission is dispersed according to some property of the particle. This is some basic definition. And now, molecular energy level, this is the most important thing. In atomic energy level, when you go to the atomic level, and this in case of atoms, the atomic energy level consists of only electronic energy level, only electronic energy level. But in case of molecule, electronic energy level. But in case of molecule, there is you see this electronic energy level, this vibrational energy level, this rotational energy level also. That is, there are three types of energy level exist in case of molecule, that is the electronic, vibrational, and rotational energy levels. And these electronic energy levels, in molecule, you see that unlike that of atom, the electronic energy level is spread due to the presence of vibrational and rotational levels. The molecule is formed by bonding two or more atoms due to covalent, ionic, or coordinate bonding and overlapping of valence shell or valence orbital. As the nuclei, two nuclei or two atoms of a molecule come closer, the overlapping of valence orbital led to the formation of the valence energy band. For example, you see this p orbital. In general, in case of atom, this p orbital is a dumbbell-like shape. But when two atoms, they come closer, and their valence orbital is p orbitals, that is two p orbital come closer, then they may form this structure. And also, not only this structure, but there are also other structures also. These two p orbitals may form. These are so another types of structure. And in this way, and this structure, when these two p orbitals, they overlap and this form, they form this pi molecular orbital. And the shape of this pi molecular orbital is like this or like this, or also there are another one types of orbital. And now one point you must note, that what is the shape of this orbital? Actually, these are some of the electronic distribution. Electronic distribution. In case of atom also, the valence orbital, it simply gives the charge or electron charge distribution. In case of molecules also, this when the excited state is a pi orbital state, our ground state is a pi orbital state, then this is the shape of this molecule. This is the shape. If it is a pi orbital, then either this is the shape of this molecule, or this is the shape of this molecule. In case of atom, this is the shape of the molecule when it's a p orbital. The valence shell is a p orbital. This is the shape of this molecule. And when a molecule goes to the excited state, then the nature or shape of this excited state, accordingly, the shape of this molecule changes. And that is, we can say that there is a change in this electronic energy level. That is when electronic energy level changes, it simply means the changing in electron cloud distribution, changes in electron cloud distribution, and that means the changes in the shape of the atom or molecule. And therefore, when an atom or molecule goes from ground state to the excited state, electronic state, of course, it simply means they are changing shape or changing electron charge distribution or spatial charge distribution, it occurs. And therefore, you see that when molecule from pi orbital is formed, then it is called the bonding state or pi state. That is when the valence shell or ground state is a molecular ground state, that is a pi orbital, and it is called the bonding state or pi state. And when it is unfilled, then it is called the LUMO state, and totally filled, that is called the homostate. And therefore, pi state, that is the homostate, pi state, that is the lumostate. And similarly, you see, this is the same in case of atoms, that is the ground state and excited state. Ground state is maximum field, and that is the homostate. And also there are several other calculations, but it's not possible to perform these types of calculations here. That is the highest occupied state, valence cell, that is called the homostate, and this is the excited state, it is called the lumostate. And there is a probability, that is when an electromagnetic wave is incident, then from this ground state, electronic state, the electrons can move to the excited state. And there, that is, we say that the molecule goes to ground state to excited state. Actually, if we say that molecule goes from a ground state to excited state, it simply means the ground state electrons in the molecule, it goes to the excited state. And as a result, the molecular shape, electronic charge cloud shape, it changes. And similarly, you see for sigma molecular orbital, in case of atomic orbital, if the two s orbitals of two neighboring atoms overlap, and as a result, this is a spherical in nature, and when those two s orbital overlap, it forms something like that of a ellipsoidal nature, and that is called the sigma orbital. And this sigma orbital, when it is filled up, it is called the bonding state or sigma state. Unfilled state, that is the sigma star state. And similarly, a molecular orbital is formed due to overlapping of d orbital, that is the n bonding, n star antibonding state. And this is for d orbital case. And now, in case of molecule, you see that electronic transition in the molecules takes place from pi to pi star, sigma to sigma star, and so on. And this is same as that of your atomic, in case of, when you consider in case of atomic levels. And now, potential energy curve, and this is the graphical representation of the potentials. Potential energy of a molecule. And this is called the Morse potential energy curve. All of you are aware, those from physics background, those from chemistry background, they all know this Morse potential energy curve. And here, for a simple diagram of this Morse potential energy curve, we see that when you consider a molecule consisting of two atoms, and one atom is considered here, and the second atom, it moves with respect to the first atom. And this is the minimum energy configuration, that is, two atoms forms a bond, and when the second atom, it keeps a distance, or it maintains a distance, and at this distance, this potential energy is minimum. And generally, these molecules like to stay in this minimum potential energy. But when this second molecule comes closer, or compression of this bond occurs, then potential energy increases in this way. And also, when this bond expands, then also potential energy increases in this way. And this is the minimum energy potential. And in this Morse potential energy, in this graphical representation of this Morse potential energy curve, you see there are several horizontal lines, and these lines represents the different vibrational level. And you see that when a molecule lies in this when an atom in a molecule lies in this equilibrium position, this is the second atom, then with respect to the first atom, this molecule cannot stay at a rest position, but it always starts oscillating. And this is the simplest form of oscillation. There may be some twisting oscillation also, but if stretching oscillation, it occurs in this way. You see that when a molecule lies in the ground vibrational level, you see with respect to this mean position, this is the amplitude. This is the amplitude of this ground vibrational level. And this is when these molecules vibrates in this ground vibrational level, it forms a stationary vibrational wave like this. And this is called a stationary waves, of course. And you see this amplitude of vibration, it starts from here to here and here. But in the excited state, this is the excited state vibrational level. Here, what happens is that when molecule goes from GS vibrational level, vibrational state or VS, VS to E or excited vibrational state, then what happens is that its vibrational amplitude increases. Vibrational amplitude increases here, you see, and as we go up and up, that is the more and more excited vibrational level, their vibrational amplitude increases. And therefore, you see that when you say that, what do you mean by this excited state vibrational level? It simply means that their vibrational amplitude increases. But unlike, you see that if we consider a macroscopic, say, oscillator like a spring system, and here this vibrator, when you just stretch it and when you just stretch it and then leave it, it also vibrates. And this vibrational amplitude, you see here, you can increase this vibrational amplitude by any continuous amount, say 1 centimeter or say 1.1 centimeter or say 1.2 centimeter, anything. And this is the continuous way of increasing the vibrational amplitude. But when you go to the molecular level, molecular oscillator, or when you go to the atomic oscillator level, then this vibrational amplitude you cannot increase in a continuous way, but in a discrete manner. Whenever some energy is given to this molecule, its vibration energy may change, vibrational energy may change, and then we may say that from vibrational ground state, a molecule may go to the vibrational excited state, and that is its vibrational amplitude increases in a discrete amount. Okay, and therefore you see that in this Morse potential energy curve, this is the molecular electronic potential energy curve, and this is graphical representation, of course. And within this electronic energy level, there are several vibrational levels, and within this vibrational level also there are several rotational levels also. And actually this rotation of molecules, it comes into effect for gaseous molecules. Mainly for gaseous molecules, the molecules may rotate, but not for solid or liquid molecules. Okay. And now you see this electronic transition in molecule takes place from the valence energy level, which is also called the ground state or E0, to any upper unfilled energy level E1, E2, E3, called the excited state energy level or the electronic energy level. And here in this figure, you see that I draw two Morse potential energy curve. One is this ground state energy level, electronic energy level, of course, that is E0. It is denoted by E0. And that other is the excited state electronic energy level. It is called the E1. And then you see both this ground state electronic energy level and excited electronic energy level, and this potential energy curve consists of a large number of horizontal lines. That is, it represents the vibrational level in the ground state electronic level energy level, and also in the vibrational level in the excited state electronic energy level. And several of these Morse potential energy curves of different energy levels are shown in this figure. And in a molecule, there are three types of energy level. I already discussed, that is electronic energy level, vibrational energy level, and rotational energy level. And this electronic energy level, its energy is much greater than vibrational, and vibrational energy level, it is also much greater than that of your rotational energy level. And typically in an electronic energy level, a large number of vibrational and rotational energy levels may exist. Now at room temperature, the molecules are in the lowest energy level or E0 energy level. And when the molecule absorbs UV radiation or electromagnetic radiation, then the molecule may go to the E1, E2, E3, actually not molecule, but the electrons, outermost electrons or valence shell electrons, they may go to the higher energy level, E1, E2, E3, and so on. And delta E equal to h nu, that is En minus E0. And electronic energy level per mole, that is 35 to 71 kilocalorie. And similarly for vibrational energy level, that is around 0.01 to 10 kilocalorie per mole. And for rotational energy level, it is very small. Now, this principle of UV Vis absorption spectroscopy, and here you see what happened is that you see these two electronic energy levels, and when some EMR of some suitable frequency, h nu, it interacts with the molecule, and then the molecule in general lies in the ground electronic state and in the ground vibrational level. In general, that is the molecular energy level in general is that is the molecule lies here. That is the ground electronic level or electronic state and ground vibrational state. But also due to some thermal agitation or thermal perturbation, the molecule may absorb some energy, thermal energy, and then the molecule may go to some upper excited vibrational level of this ground state electronic level. And now when some electromagnetic energy interacts, is incident on this and interacts with this molecule, then they absorb this photon energy and they may go to any directly. This transition takes place directly to any vibrational level of this upper electronic energy level. You must note that molecule from this ground electronic energy level and ground vibrational level, and that is called 0, 0 level. That is this first 0, it stands for ground vibrational level, and second 0, it stands for this is the ground electronic energy level, and this is the ground vibrational energy level. And therefore you see that from this, hello, am I audible?
Yes, sir, you are audible.
Okay. And therefore, you see from this ground electronic energy level and ground vibrational level, that is second 0 stands for ground vibrational level, the molecule may go to first excited electronic energy level, that is 1. At any vibrational level of the excited state, 1n. That is, the molecule may go to any vibrational level. But when the molecule goes to any vibrational level, maybe that upper vibrational level, and this transition takes place directly. That is, there is no changes. If you see, consider the second atom here, and this is the first atom, and there is no changes in this direction. That is this amplitude or this changes of distance or bond length of the first and second atom, it remains same. And this transition, electronic transition, takes place in this way. And that is, it goes directly to the excited electronic level and any vibrational level which comes directly in contact with it for this direct vertical transition. And as a result, you see the molecule may go to any upper vibrational level, but the molecule cannot stay in this upper vibrational level. It non-radiatively relaxes to the ground vibrational level of the excited state. This molecule non-radiatively relaxes to the ground vibrational level of the excited electronic state. And from this ground vibrational level of the excited electronic state, then transition occurs. Again, electronic transition occurs to the ground state, and that is called the fluorescence. That I will discuss later. But what happened here, you see that from this ground vibrational, ground electronic energy level and ground vibrational energy level to electronic transition takes place to the first excited electronic transition, electronic energy level, and any vibrational level, nth vibrational level. That n may be 0, 1, 2, 3, etc. And therefore, as shown in this figure 5, each molecular energy level is occupied by a number of vibrational levels as shown in this figure by dashed horizontal line, and these are the dashed horizontal line in this Morse potential energy curve. And also between two vibrational levels, several rotational levels are occupied, not shown in this figure. Now, generally, UV Vis absorption process. Generally, at room temperature, the molecules lie in the lowest vibrational level of the ground electronic state. That is called 0, 0 level that I already mentioned here. This is the 0, 0, that is the ground electronic level and ground vibrational level. And this first 0 stands for ground state electronic energy level, and second 0 stands for lowest vibrational level of the ground state electronic energy level. And different vibrational levels correspond to ground state electronic energy level, that is denoted by 0, 0, 0, 1, 0, 2. This first 0 means ground state electronic energy level, and this 1 means ground state electronic energy level and first excited vibrational level. This is the second excited vibrational level. This is the ground state vibrational level. And now, when an EM radiation of suitable frequency is incident on a sample, and then the molecules interact with the electric field of the EM radiation and absorb energy, and then from 0, 0 level, the molecule can go to any vibrational level of the excited electronic state that I already discussed. Any vibrational level of the excited electronic state. That is, the molecule may go here, here. Also, there is one principle that I will also discuss in this respect. Now, different vibrational levels of this excited state electronic states are denoted by 1, 0, 1, 0, 1, 1, 1, 2, and so on. And thus, when a molecule absorbs energy from EM radiation and then following transitions may occur, that is the 0, 0 to 0, 1, 0, 0 to 1, 0 transition, that is transition from 0 vibrational or level of ground state to 0 vibrational level of the excited state. That is, and this transition is also called the 0, 0 transition in absorption spectroscopy. And you see that whenever you will see any absorption spectrum, you see this is the absorbance, ABS, that is the absorbance, and this is the lambda, and this plot. And in this plot, the longest wavelength band, and that is called the 0, 0 band, that I will also show you later part. That is, and here this is called the 0, 0. Therefore, first of all, you have to mark this 0, 0 band in your absorption spectrum, and it simply means that is the transition from 0, 0. You see this 0 vibrational level of the ground state to 0 vibrational level of the excited state. Now, this is also denoted by 0, 0, 0 transition. And you see that also there is another transition, that is 0, 1 transition in absorption spectroscopy, and so on. And similarly, the 0, 0 to 1, 1 transition, that is the transition from 0 vibrational level of ground state to first vibrational level of the excited state, and that is denoted by 0, 1. And this 0, 1 transition, you see that the next peak, it is the 0, 1 transition. We just denoted 0, 1. And different transition gives different peaks in the absorption spectrum, and the most probable transition is followed by Frank-Condon principle, that I will also discuss. And this peak may be 0, 0 transition or 0, 1 transition or 0, 2 transition, etc., depending on the molecular structure as well as also the association or aggregation of the large number of molecules. And whether and sometimes it is also found that the molecular excited electronic states are deformed due to the association or aggregation of large number of molecules or formation of dimers, trimers, tetramers, even polymers. And therefore, the excited molecular electronic energy levels, they are distorted. And as a result, this maybe that sometimes you may not find this 0, 0 transition, maybe that you find this 0, 1 or 0, 2 transition, etc. Now, Frank-Condon principle, you see, this is the most important principle when you want to discuss this absorption spectroscopy. This is the important principle, one of the important principles. And its definition is that is since the electronic transition occurs very rapidly, and therefore the vibration and rotation of the molecules do not change the internuclear distance appreciably during the transition. It simply means, you see, that when transition takes place from this ground state to the excited state, then it occurs, this electronic transition occurs so rapidly. Therefore, then this is the first atom, this is the second atom, and there is no changes of this nuclear configuration, that is changes on this bond length between the two nucleus. And that is, there is a direct vertical transition takes place from ground electronic state to excited electronic state, and there is no. But you see, in this case, here is the here you see that in this case, if the excited electronic state is shifted slightly, and therefore this transition from this ground electronic state, it occurs to the first vibrational level. That is the 0 vibrational level to directly, there is a transition to the first vibrational level of the excited electronic state, and that is called the 0-1 transition. Therefore, in this case, the 0-1 transition is the most probable transition, and this UV Vis spectrum, you will find that the intensity of this 0-1 vibrational peak, this is the most intense peak, but this 0-0 transition peak, that is the longer wavelength peak, this is the intensity is very small, and same as that is with 0-2, 0-3, and so on. And these are the diminishing intensity. That is the maximum intense peak will be the 0-1 transition. That is this that is this electronic transition occurs so rapidly, there is no changes in this bond length, and as a result, there is no vibrational transition or rotational transition. And similarly, here in this case, you see this due to deformation of this excited electronic state, or deformation of the molecular structure, or aggregation of molecular structure, or formation of dimer or trimer, etc. There may happen a lot of things. And this excited electronic state is shifted to the right side. This excited electronic state is shifted to the right side so that this position does not match exactly with this position. And as a result, when this electronic transition takes place from this ground state, it goes to 4th vibrational level of this excited state. 4th vibrational level of this excited electronic state, and therefore this transition occurs 0-4 transition. And this is the most probable transition, and is a 0-4 transition. And in this case, you see that 0-4 transition, we say 0-4 transition, this is the intense peak, intense vibrational peak will occur here, 0-4 transition. Other vibrational peaks have less intensity. And this is the main basic of Frank Condon principle, that is, the electronic transition occurs so rapidly that vibrational and rotational level does not change. That is, there is no change of this internuclear distance appreciably. And here, I am again discussing it in some elaborately. That is, you see, I am drawing, I just draw here these 3 figures here, exactly match this excited electronic energy level, exactly matches with the ground state electronic energy level. Therefore, 0-0 transition is the most probable in this case. Here it is shifted a little bit. Here it is shifted a little bit, and therefore this 0-1 transition is the most probable. And here you see that 0-4 transition is the most probable. That is, excited state, electronic energy level is shifted more. And generally, actually, what happens is that when this shifting occurs, it is shifted to the right side with respect to the ground state. Okay. And now, you see, in this figure, this is one spectrum, UV Vis spectrum. That is, when you use some UV Vis absorption spectrophotometer and take a UV Vis spectrum, you will find this type of UV Vis spectrum. That is, there may be, not all, but there may be several vibrational peaks. There may be several vibrational peaks like this. And in this vibrational peak, you see this is the 0-0. First of all, you have to mark this 0-0 transition, and this is the longer wavelength transition. That is, this wavelength is maximum in comparison to other vibrational peaks. Generally, maybe that you may not find all these peaks. Maybe that you may also find this vibrational, like this also. And there are different types of things, and this is the then you have to mark this peak as a 0, 0 peak. Okay, and if only this peak exists, then you have to mark it as 0, 0, 0, 1 peak. And this is the absorption spectrum from the ground state to the fast electronic energy level, and there are several vibrational peaks also. Now, different types of electronic transition. Here I show schematically different types of electronic transition. That is, you see sigma sigma star, pi pi star, n sigma star, n pi star, n sigma pi star, pi sigma star, and these are discussed in detail in these Rohatgi Mukherjee books and also in several papers. You may check it. And now the sigma sigma star transition. This is mainly in case of methyl, this CH bond. And this transition occurs say around, this is the actually this absorption maximum is falls in the UV range, that is 125 nanometer. This pi pi star transition it occurs in case of alkanes, alkynes, carbonyls, and 107 nanometer to 205 nanometer in sigma star. It occurs in this 150 nanometer to 250 nanometer, even in the visible range in general. But you see that around this n pi star transition, it occurs in the visible range. 300 nanometer sigma pi star, pi sigma star transition, and actually these are not theoretically possible, but not experimentally. These are not observed. And mainly the n pi star, pi star transition we find. And this n pi star and pi star transitions, these are observed above 200 nanometer, and these are accessible by UV Vis absorption spectrophotometer. This pi star transition, n pi star transition. Generally, using this UV Vis absorption spectrophotometer, you get only these two types of electronic transition. And that another important thing is that Lambert law. That is, it occurs in case of a liquid and liquid samples, of course. But in case of this thin film, or this law is not applicable, then this is the basic law for this liquid samples or any solution samples. And when you see that this is a sample holder, maybe that 1 ml sample it may contain. And now when this I naught intensity of any monochromatic radiation, say H nu, it is incident here, and some part of it is absorbed. And then when it goes in 180 degree, you see this angle is 180 degree of the incident ray and transmitted ray. This angle is 180 degree. That is, after 180 degree, when we put here any monochromator here, we can detect this I. That is, and therefore you see this is the after absorption of some radiation, some intensity of this radiation, and this is the I. This is the transmitted intensity, and this is the incident radiation. And now it says this Lambert law. It states that if X be the thickness of the solution at any point, then minus di dx proportional to I. And you know this types of relation in case of radioactive materials also. In radioactivity, you also find this types of relation. That is radioactivity, and that is at any distance x. That is at any distance x, the rate of change of intensity minus di dx, or rate of decrease of intensity minus di dx, it is proportional to I. That is the intensity at that point, and minus di dx equal to k into chi, k into I, and that k is the proportionality constant. Now integrating between the limit, we find that ln I by I naught equal to minus kl, or it is converted to log scale. Actually, there is a mistake here. Actually, it should be I naught by I, and it should be plus. And then you see that I naught by I, that is equal to A, and this is the absorbance. And that is log of I naught. This is the incident radiation by I, and that is called the absorbance. And this is the absorption coefficient. and therefore this absorbance A equal to E into L. And now here later on it is modified by BRs, and then it is called the Lambert-Beer's law in a total, and BR added here the concentration of the sample. And this BR law states that this intensity, decrease of this intensity, it is in proportional to the intensity of the incident radiation and concentration of the solution. That is minus di dx, it is proportional to C into I also, C into I. And C is the concentration in molar concentration. Therefore, minus di dx, that is equal to K into C into L. K is the constant. And then integration, and we get log I naught by I, that is equal to K by 2.303 into C by L, and it is called absorbance. And A equal to, actually, A equal to E into C into L. And what we measure in this absorption spectroscopy corresponding to any wavelength, that is the absorbance. And here in this spectrum, you see that this, we just gradually change the wavelength of the incident light and measure this absorbance. And the intensity we measure, we find the absorbance in different way, and we get a spectrum like this. That is, we this change when this electromagnetic wave is incident, we gradually change the intensity of this electromagnetic wave, gradually change and measure this absorbance. And then we plot this graph. And this is called the absorption spectrum. A spectrum, this is called the spectrum of UV Vis absorption spectroscopy. Okay. And this is also called this A, it is called the absorbance or optical density also. That is log of I naught by I. I naught by I. And here also you see that A, that is the absorbance versus concentration plot of this Beer-Lambert law. It gives a straight line, but there is a deviation. You see that in case of when you want to measure the solution of a liquid, a solution of a sample, then first of all you see the absorbance intensity of different peaks. It gradually increases when you increase the concentration. This C is the concentration, and it gradually increases. But after a particular concentration, you see then again this absorbance or intensity, absorbance of this fluorescence spectrum, it gradually decreases also. And that is called the quenching, we may also say. Therefore, when you want to take the UV Vis absorption spectroscopy of a solution, you have to fix the optimum concentration. You have to fix the optimum concentration, because below optimum concentration, the absorbance is less, and above optimum concentration, then also the absorbance is less. And depending on your application, you may also study less concentration, but mole concentration of solution, this deviation occurs, and this is due to closer association of molecules at higher concentration. And now it influences the formation of molecular aggregates, resulting in the decrease in absorbance. Beer-Lambert law is valid in the ideal case of solution state, where there is no interaction in the solute molecules with the solvent molecules, and possibility mostly in case of non-polar solvent. This Beer-Lambert law is valid. And also during this absorption measurement, no chemical reaction absorption takes place in the solvent of the liquid case, but reaction kinetics. But for research purpose or any experiment purpose, you may also study the reaction kinetics. That is, with the passage of time, you may also take several, say maybe that after 15 minutes or after 10 minutes interval, you may take the absorption spectrum to check whether there is any chemical kinetics or chemical reaction takes place in the solution phase. Even in thin film also, you may observe the changes in this absorption spectrum after several days. That is, there is some molecular aggregation. And even in case of nanoparticles also, if we just keep the if you prepare a nanoparticle thin film and keep it for several days, then also you may change. You may observe the change in this absorption spectrum. That is, there is some agglomeration, there is some aggregation of these nanoparticles or molecules. And pH and temperature of the solution should remain constant during the experiment. And now chromophore. Chromophore are the parts of the molecules or radial which impart color to the sample, and this color means they emit light in the visible range. For example, various aldehydes, alcohols, acid, you see phenyl rings, and when more than 2 phenyl rings are attached to a sample, they give fluorescence to the visible range. And generally, heavy chromophore, when you add it to a sample, to a molecule, then this absorption spectrum is shifted to the visible range, of course, to the higher range, of course, and these are called the dye. Say, intense fluorescence you may also observe in case of in the visible range. And this fluorescence in the visible range occurs due to pi star transition, and it produces color. And whenever some chromophores are added, generally this pi star transition occurs, and then it fluorescence, it is shifted to the visible range. Absorption is also shifted to the visible range. And when double bond, triple bond triple bond exists to a molecule, then fluorescence is shifted to the visible range. That is C triple bond N, C double bond N, C triple bond N. It is connected, say C triple bond N, it is connected here, then the absorption spectrum is shifted. Absorption spectrum, fluorescence spectrum, both are shifted to the visible range. To interpret the UV Vis spectrum, following points should be noted. That is the actually there are some various research papers, and these types of discussions has been done a lot of things. That is non-conjugated alkanes. It shows the intense absorption below 200 nanometer and therefore inaccessible to UV Vis spectrophotometer. Non-conjugated carbonyl group compound give a weak absorption band in the 200 to 300 nanometer, and that is acetone has 279 nanometer lambda max. And there is cyclohexane and others. Now, oxochrome, you see the functional groups attached to a chromophore which modifies the ability of the chromophore to absorb light, altering the wavelength or intensity, that is called the oxochrome. And now, in case of absorption spectrophotometry, these are important, that is the intensity and shift. There are four types of shifting, that is the bathochromic shift or red shifting. Red shifting occurs of the absorption spectrum with respect to the solution phase. Even you see that when you want to take the absorption spectrum in the thin film or in the solid state powder sample, then with respect to the solution spectrum, there is a rate shifting or longer wavelength shifting of the absorption spectrum, that is called the bathochromic shift. When any chromophore is attached to the original mother molecule, then also there is a high probability of this bathochromic shift. But also that another important thing is that this hypsochromic shift or blue shifting of this absorption spectrum. And generally, it is observed that whenever there is some H aggregate occurs, molecular H aggregate occurs in this solid state or thin film, then this absorption spectrum is shifted to the blue shift. And also there is also hyperchromic shift, hypochromic shift. Hyperchromic shift means the intensity of this absorption band increases. Hypochromic means intensity of the absorption band decreases. And this bathochromic shift, this effect is due to the presence of an oxochrome or by the change of solvent also. And oxochrome group like OH, CH3 causes absorption of the compound at longer wavelength. Also pH effect. pH effect also shifted to the red shifting occurs. And here you see, this is the hyperchromic shift, that is the intensity increases, and hypochromic shift, that is the intensity decreases, and this is the red shifting, and this is the blue shifting. application of this UV Vis absorption spectroscopy, that is a qualitative and quantitative analysis. And it can be used to find the molar concentration of the solute under the study, detection of impurity. Detection of impurity, detection of, say, whenever there is some impurities present in some organic solvents or organic molecules, or chemical samples, even in case of inorganic materials, nanoparticles, there is some impurities present, it can be, then this absorption spectrum, it changes. And just by observing the changes in this absorption spectrum, you can say how much amount of this impurity or what types of impurity may present in the sample. And also detection of different isomers. It is also possible. Determination of molecular weight using this Beer's law. And then you see, this is a simple construction of a UV Vis absorption spectrophotometer. It costs around 5 lakhs to some far higher, maybe that 5 lakhs. And for 5 hours, for FIR, it may cost say around 25 lakhs. But 5 lakhs UV Vis instrument, it is enough for this research purpose of this thin film nanoscience research purpose. And here you see, that is for measuring the liquid sample. You see there are 2 holders, and this is the reference solvent. And any solution, it is called the sample. Any solution of any sample you have to put here, and that solvent, pure solvent, you have to put here. This is called the reference level. And when this intensity, you see this intensity of this light, it is equally divided of I naught intensity, and this intensity, it goes to the reference level and detector. For it has been taken, it has been measured by this detector for reference level, and I, this from the sample, some of the intensity is absorbed, and then this is the transmitted intensity is I, and it is also taken or measured by this detector. And then by comparison it and take this log I naught by I, this is the absorbance and versus wavelength. And here you see a monochromator, it's a grating, and this grating is gradually rotated to change the frequency of this incident light. And therefore frequency or wavelength of this incident light, and therefore you see just by gradually in this graph, you see that different corresponding to different wavelength of this different wavelength of the incident light, this absorbance is taken, and this plot of this absorbance corresponding to different wavelength are taken, and this is called the absorption spectrophotometer. Okay, and this is the all that this is in a nutshell this absorption spectrophotometer discussion. Now I am discussing this fluorescence spectrophotometer or fluorescence spectroscopy. And fluorescence spectroscopy, that is when a molecule is excited by UV or visible light, and then electronic transition occurs and the molecule goes from ground state to excited state by absorbing the EMR, and this phenomenon is called the absorption. And discussed in this part of UV Vis absorption spectroscopy. Okay. Now in the excited state, the molecules cannot stay long. And in the excited state, that molecules may stay of the order of 10 to the power -6 to -5 seconds. And molecule comes down to the ground state. And here you see that when an electromagnetic wave of excited of h nu, it is absorbed when a molecule is initially lying in the ground electronic state and ground vibrational, that is the S0 state, S0 state. And when some electromagnetic radiation is absorbed by this molecule, it goes to the excited electronic state. That is the S1 state. S1 means singlet state. S0 means singlet ground state, and it is a singlet excited state. Then there are several, but the molecules cannot stay in the excited state for a longer time. It must relax to the ground state. That is, it must come down to the ground state. And this coming down to the ground state, it occurs by several processes. It may occur by intersystem crossing. It may occur, the most frequently occurs case is that the fluorescence emission, H nu prime. Here you see that H nu, it is absorbed, this amount of energy is absorbed, it goes to the excited state, S1 state. And from this S1 state, it may relax to the ground state by emitting a photon of frequency nu prime and energy H nu prime. That is, it absorbs this H nu energy and emits fluorescence of H nu prime energy. And of course, this nu is greater than nu prime. That is, the fluorescence frequency is less than the absorption frequency. First thing it may occur. And second thing is that when there are large number of molecules comes to the excited state, and if that molecule, some triplet state exists in that molecule, there may be some inter-system crossing. Of course, that triplet state, the energy of this triplet state is comparable to the energy of the excited singlet state, S1 state, comparable. And therefore, there may be direct transition from this S1. Some of the molecules may come down from excited singlet state to the excited triplet state. And then you see from this triplet to singlet, ground state S0 transition occurs. And that is called the phosphorescence transition. And this, you see that from triplet to singlet transition, it is prohibited. Theoretically, mathematically it is prohibited, and therefore there is a little possibility of this transition, and therefore this transition lifetime is much, much higher. And as a result, what happens is that this fluorescence emission, it occurs, it lasts, say, from millisecond to several seconds also. And you know, and that is called the phosphorescence. That is, you just phosphor a material by using a light and then keep it in the dark, it emits phosphorescence for several seconds. And that is called that is the transition from triplet to singlet ground state. And also that another thing is that fluorescence, and that another thing is the quenching. Quenching means when there is a concentration of the molecules increases, or in the solid state, the molecules collide with each other. And as a result, the molecules in the excited state, when there are several molecules in the excited state, they may collide with each other, they relax this energy and come down to the ground state without any kind of radiation. Just by thermal radiation, they just collide and relax this energy and come down to the ground state. And that is called the quenching. And therefore, you see that whenever the concentration of molecule in the solution state increases, or whenever in some cases, whenever a large number of molecules come closer in the solid state and their organization is random in nature, therefore, this molecule, there may be some vibrational collision also occurs, and the molecules collide with each other, some vibrational relaxation occurs, and therefore some quenching occurs. That is, the molecule relaxes to the ground state non-radiatively, and therefore the fluorescence intensity decreases to a large extent. And mainly this type of quenching occurs in solid state. This type of quenching occurs mainly in case of H type aggregates occurs. In J type aggregates, generally this quenching occurs very little. But in H types of aggregate, quenching occurs to a larger extent, and most of the cases, the fluorescence, we do not get any fluorescence emission in thin film when there is H types of aggregation. And also in solution state, when large number of concentration becomes larger, then also molecular collision occurs, and then quenching occurs and fluorescence emission decreases. And also that another possibility is that energy transfer. That is, whenever there is some impurities mixed, you see, suppose there is one type of molecules, say A types of molecules, and in these A types of molecules, if we just mix some other B types of molecules, then when this A types of molecules goes to the excited state, but B types of molecule remains the ground state, then this excited A molecules, it reacts with these B types of molecules and gives energy to the B types of molecules, so that B types of molecule goes to the excited state and A types of molecules come down to the ground state. As a result, you see that B types of molecules go to the excited state and then again relaxes. And therefore, this fluorescence emission, and that is called the energy transfer. And as a result, this fluorescence emission changes. And this property, this energy transfer property, it can be used as an effective way of optical gas sensor. And we also reported several papers based on this energy transfer, or sometimes it is also called the FRET, or fluorescence resonance energy transfer, FRET. And based on this FRET, we have designed several sensors like arsenic sensors. We reported several of these sensors, and also several other sensors based on this optical sensor, based on this energy transfer. That is, when you sense some arsenic impurity in our sample, and then this energy transfer occurs, and as a result, what happens is this: the fluorescence wavelength changes, or fluorescence. That is, if suppose this is the fluorescence intensity, and this is the fluorescence spectrum. And initially, without any kind of impurity, if this is the, say, suppose fluorescence spectrum, and when the impurity is added, suppose some arsenic, we add here some arsenic contaminated water, and then what happens is that there is some energy transfer occurs, and these types of fluorescence is shifted to the longer wavelength. And as a result, this color changes. Color changes, say from blue to green, or to yellow, or to red. This type of fluorescence changes, and sometimes you can directly observe this change, or sometimes you have to take this fluorescence spectroscopy to observe this change. And then these types of sensors can be designed based on this FRET, or fluorescence resonance energy transfer, or simply by energy transfer processes. And now this fluorescence process, and in this process the transition occurs from the excited singlet to ground state singlet. That is, the molecules can partially dissipate energy by undergoing conformational changes and relax to the lowest vibrational level of the excited state that I am discussing. I am discussing detailing in the Morse potential energy curve. Okay, I already discussed it. I already discussed this quenching energy transfer. Now, Jablonski diagram. And here you see that when in general the molecule lies in the ground electronic state of the ground vibrational level, that is the S0 state, that is the singlet ground state. And when some energy, electromagnetic energy is incident, then it goes to the S1, that is the first excited electronic energy level, or second S2 state electronic energy level. And then what happens is that there is some internal conversion occurs. That is, from the different upper vibrational level, it relaxes to the ground vibrational level. And sometimes from this excited second excited electronic energy level, it may relax to the first excited electronic, or S1 energy level, and also relax to the ground vibrational level of the excited electronic energy level. And then you see all the molecules comes down to the ground vibrational level of the excited electronic state. And then if the triplet state, the energy level of this triplet state is comparable to the S1 electronic state, singlet electronic state, then sometimes, and whenever there are a large number of molecular population in the singlet state, then some intersystem crossing may occur, and some of the molecules may go to the triplet T1 state. And also other molecules in this S1 singlet state, it relaxes to the ground S0 state, again from this ground vibrational level of the excited electronic state to any vibrational level of the ground electronic state level. And as a result, we get this fluorescence emission. Therefore, you see that whenever there is absorption occurs, and there is a corresponding fluorescence occurs also, and sometimes phosphorescence occurs also, but not always, of course, but sometimes phosphorescence may occur. Therefore, when the molecules absorb photon energy of incident EMR having suitable frequency, then the molecules go from ground state to any excited singlet state, S1, S2, etc. And this phenomenon of molecular transition from ground state to excited electronic state, GS2 ES, it is called the absorption. But the lifetime of the molecules to remain in the ES singlet state is very small, of the order of 10 to the microsecond to picosecond, to nanosecond. And thus the molecules immediately try to relax to the ground state. Now, generally from higher order ES, that is S2, molecules come down to the lowest ES, that is S1, by non-radiative transition, and actually the molecules come down to the lowest vibrational level of the ES. And then if the molecules come down to the ground state from ES, that is S1 to S0 transition, and by emitting a photon, then this transition is called fluorescence. And I already showed this in this Jablonski diagram, that is the ground vibrational level. This transition takes place directly to the S1 to S0 transition. It is called the fluorescence emission. Okay. And however, and if the molecules come down to GS2S by emitting a photon, this transition is called the fluorescence, and this occurs within a lifetime of 10 to the power minus 6 second to 10 to the power minus 9 second. And that is called the fluorescence lifetime. And there is also instrument to measure the fluorescence lifetime, nanosecond or microsecond or picosecond order lifetime. But however, sometimes also it occurs that if the energy of the excited state singlet S1 is comparable to the excited state triplet T1. Then for some molecules, non-radiative transition occurs from S1 singlet to T1 triplet state as shown in the Jablonski diagram, and this phenomenon is called the intersystem crossing or ISC. And then from excited state triplet, the molecules may come down to the ground state singlet by emitting photons. And this phenomenon of triplet to singlet transition is called the phosphorescence emission. And here I already discussed it. From the singlet state to triplet state, this intersystem crossing occurs, and then from this triplet state, there is a transition to the ground state, that is T1 to S0 transition. T1 to S0 transition, and it is called the phosphorescence emission. And this phosphorescence, since this triplet to singlet transition is theoretically forbidden, and therefore this transition occurs, and therefore the lifetime of this transition is millisecond to several seconds. And therefore we get phosphorescence for a longer time, over several seconds. Now, explanation of fluorescence spectrum in terms of the energy level diagram. In a molecule, the electronic absorption takes place when electronic transition occurs from ground state to excited state by absorbing photon energy of incident EM radiation. But the excited state lifetime of this molecule is very, very small, and therefore the molecule relaxes to the ground state. And here in this figure, you see, here also I just represent two Morse potential energy curves. One is the ground electronic state, and other is the excited electronic state. These are the two Morse potential energy curves. And this horizontal line, as I already discussed, these represent the vibrational energy levels. Now, when absorption takes place, you see this is the H nu. And when absorption takes place, then the ground vibrational level, the molecules go to the when EMR radiation is absorbed by the molecule, then the molecule goes to the any vibrational level of the excited electronic state. And from this excited electronic state, any vibrational level of this excited electronic state, the molecules relax to the ground vibrational level of the excited electronic state. And from this ground vibrational level of the excited electronic state, then this is the non-radiative transition, that is only heat energy developed. And then from this ground vibrational level of the excited state, this transition occurs, radiative transition occurs. That is called the fluorescence emission, H nu. Or we may say it is the H nu prime. This is the fluorescence emission. This is the H nu, this is the incident light, and then we get H nu prime. This frequency is nu prime. And then from this ground vibrational level of the excited electronic state, the radiative transition occurs to, and the molecules come down to the ground ground electronic level, and any vibrational level of the ground electronic level. And then non-radiative transition occurs. Non-radiative transition occurs, that is the heat energy is radiated, or thermal energy is radiated, and then molecules come down to the ground electronic energy level. Actually, we are saying that molecules come down to the ground electronic energy level, but actually what happened is that the electrons from the LUMO state comes down to the HOMO state of the molecule. And then this non-radiatively, this relaxes to the vibrational level non-radiatively and comes to the ground vibrational level. But of course, you see from this ground vibrational level, the the radiation radiates fluorescence emission and may come down to any vibrational level of the ground electronic level. Here I show only one transition, but it may come down to any vibrational level. Okay, and this is called the fluorescence emission. And therefore, this fluorescence emission is just opposite to the absorption emission. But also you see that this frequency, it is a new, but this frequency also changes. It is a new prime frequency. And this transition, when this absorption takes place following the Frank-Condon principle, that is, there is no changes in the internuclear configuration. But then it comes down, relaxes non-radiatively to the ground vibrational level of the excited electronic state, and then it emits fluorescence and comes down to any vibrational level of the ground electronic state. And that is called the fluorescence emission. Okay. I already discussed it, and in this figure 3, I already discussed all these things. And then, even in this fluorescence emission occurs, you see that we get several such emissions like 00, 01, 02 transition, etc. That is, you see, this is the excited state, and fluorescence occurs from this when the molecules come down to the ground vibrational level of the excited electronic state. And here from transition occurs. And this 00 transition occurs means when the molecules come down directly from the ground vibrational level of the excited electronic state to the ground vibrational level, from the ground vibrational level of the excited electronic state to the ground vibrational level of the ground electronic state. This is called the 00 transition. When the molecules come down to the ground vibrational level of the first excited state to fast vibrational level of the ground electronic state. This is the and this transition is called the 01 fluorescence transition. When the molecule comes down from this 0 to 2 transition occurs, and this is called the 0 to 2 fluorescence transition. And that is the 00 transition fluorescence. In fluorescence emission, 00, 01, 02 transition occurs. Just like in case of the UV Vis absorption spectroscopy that I already discussed. Therefore, you see that when you take the fluorescence spectrum, you see also, just like the absorption spectrum, you see this 0, 0, 0, 1, 0, 2, etc. And this 0, 0, the wavelength of this 0, 0 peak, it is the minimum in comparison to other 0, 1. This is the 0, 0 transition fluorescence. This is the 0, 0. This is the 0, 1. This is the 0, 2. This is the fluorescence spectrum. And in case of fluorescence spectrum, just like the absorption spectrum, you will find these different vibrational peaks. And here in this fluorescence spectrum, this is the 0, 0 is the lowest frequency or lowest wavelength, that is the highest frequency. Why it is highest frequency or high energy? This is the highest energy transition. 0, 0. Why this? In case of fluorescence, this is the highest energy transition because you see from this ground vibrational level of the excited state, this transition takes place to the ground vibrational level of the ground electronic state. And this is the transition length is maximum and therefore energy is maximum. Therefore, 0, 0 fluorescence transition, the energy is maximum in comparison to 0, 1, 0, 2, etc. And therefore, this 0, 0 fluorescence peak, this is the minimum wavelength fluorescence peak of high energy fluorescence peak, and then 0, 1, 0, 2, etc. Now, but also you see that when you consider the absorption spectrum, in case of absorption spectrum, this is called the absorbance and this is called lambda, and then we see we get these types of peaks, and this is the 0, 0 peak. This is the 0, 1, this is the 0, 2, etc. That is, in case of absorption spectrum, this 0, 0 spectrum is the smallest energy or longer wavelength peak. But in case of fluorescence spectrum, this 0, 0 is the shorter wavelength or high energy peak. This is the basic difference between this absorption spectroscopy and fluorescence spectroscopy. That is the, in case of absorption spectroscopy, this 0, 0 band is a longer wavelength band, and in case of fluorescence spectroscopy, this 0, 0 band is a shorter wavelength band. Okay. Now, when high energy or smaller wavelength EM radiation is absorbed by the molecules, then the molecules may transit to second or higher excited state. But in all such cases, the non-radiative transition occurs in the vibrational level within a single excited state, following the proper vibrational selection rule. Now, another important thing is that the Casas rule, that is experimentally, when you want to take the fluorescence spectrum, then generally it is observed that irrespective of excitation wavelength, and suppose that I am discussing here, that is, I am just giving this explanation by showing some spectrum. Yes, you see, in this case, you see this absorption. This is the absorption spectrum, and this is the fluorescence spectrum. Okay. In practical sense or experimental sense, we have taken this absorption spectrum of a sample, and then corresponding fluorescence spectrum has been taken, and these two are plotted on the same graph. On the left side, it is given the absorbance, and on the right side, this is the fluorescence intensity. And this is the wavelength. And you see here, this is the absorption spectrum. This absorption spectrum consists of several bands, and this is a longer wavelength. This is called the 0, 0 band. And in case of fluorescence spectrum, this shorter wavelength, it is the 0, 0 band. In general, this 0, 0 band should overlap, but not it occurs. There is a slight shifting of this fluorescence 0, 0 band. And other bands 0, 1, 0, 2, etc. And then also you see that to obtain this fluorescence spectrum, you have to strike the sample with a suitable absorption frequency. That is called the excitation wavelength. You see here, you may just strike this sample with a particular 0, 0 wavelength EMR radiation. That is, first of all, what we have to do to take this fluorescence spectrum, what we have to do that, we have to incident some particular frequency, say 0, 0 band frequency of a electromagnetic radiation, EMR on this sample, and then this fluorescence occurs, and we get when we just scan this wavelength for different wavelength, we get this fluorescence spectrum. But the most important thing is that you may strike it at this 00 band, or you may strike it, or we may choose this 01 band or 02 band, no problem. Or even you may strike it from any wavelength here also. Then you also get the same fluorescence spectrum. This is the basic. Actually, this is called the Casas rule. You may strike any position of this absorption spectrum. You get the same fluorescence spectrum. You may consider any excitation line or excitation wavelength of this absorption spectrum, then you get the same fluorescence spectrum. And this is the Casas rule. And here it is this Casas rule is explained by using this fluorescence spectrum diagram. And here you see that if you just consider this light, then this molecule goes to the upper vibrational level of this excited electronic state, and then from it relaxes non-radiatively and comes to the ground vibrational level of the first excited state. But also you see that if this wavelength is greater or frequency is small, that the molecule may not go to the upper excited, topmost excited vibrational level, but it may go to some other lower vibrational level of the excited electronic state. Therefrom also it may relax to the ground state. But then also you get the same fluorescence. Yeah. And therefore you see that whatever wavelength you may strike, it may go to the upper excited state, but excited electronic state, but may go to any vibrational level of the excited electronic state, depending on the frequency of this incident electromagnetic radiation. Then relaxes non-radiatively and then gives the same fluorescence emission. Therefore, we need not have to worry about the excitation wavelength. We may strike the sample in any frequency or any wavelength, that is, which falls in the range of this absorption spectrum. You may strike in this 00 position, you may strike here, you may strike 01 position, or you may use any wavelength, and then you get the same fluorescence spectrum. But of course, you see that you may not choose any, you must not choose any wavelength of this EMR radiation, incident EMR radiation corresponding to wavelength, because here this absorption peak intensity is very small. Therefore, you won't get any fluorescence spectrum. At least you have to choose here or here. Then you get this fluorescence spectrum. And this is called the Casas rule. Okay. I already discussed it. And therefore, following Casas rule, we may say that for any excitation wavelength or striking wavelength of the absorption spectrum, we get the same fluorescence spectrum. And in real case, when you perform any experiment for the measurement of the fluorescence spectrum, the striking wavelength should be chosen from the absorption spectrum in such a way so that the striking wavelength should be always less than the 00 absorption spectrum. And of course, you see that we always avoid the striking wavelength at this 00 band, because there is a direct light will enter and you won't get this fluorescence spectrum. You always have to strike from some lower wavelength or high frequency. You have to choose always some high frequency electromagnetic radiation or striking wavelength for some wavelength or high frequency. And therefore, and it is because that you must not choose this 00 absorption peak, because to avoid the direct light on the fluorescence spectrum, to reduce the background emission in the fluorescence spectrum. In case of nearly coincidence of the 00 absorption and 00 fluorescence band, to get distinct 00 fluorescence band, the striking wavelength should be little less than the 00 absorption band. The Stokes shift, and that another important thing is that the 00, in most of the cases, it is observed that the 00 absorption band and the 00 fluorescence band, they do not coincide. the fluorescence 00 band is at a longer wavelength or less energy than the 00 absorption band. The shifting of this fluorescence band to the longer wavelength side, it is called the Stokes shift. And actually, you see here also, this is the 00 band of this fluorescence emission, and this is the 00 band of this absorption spectrum. This is the fluorescence spectrum 00 band, this is the absorption 00 band. And actually, you see the fluorescence 00 band, it is shifted to the longer wavelength in comparison to the 00 absorption band. There is a shifting of this fluorescence band, and they do not coincide. But in some cases also it is observed that 00 band coincide, but in most of the cases this 00 band has been found not to coincide, and this is called the Stokes shift. And there is some explanation. In most of the cases, it is observed the 00 absorption band and the 00 fluorescence band do not coincide. The fluorescence 00 band is at a longer wavelength, and then the 00 absorption band. The shifting of the fluorescence band to the longer wavelength side in comparison to the corresponding absorption band is called the Stokes shift. As shown in figure 7, this 00 fluorescence band is at a longer wavelength than that of the 00 absorption band. You see here also, this is the fluorescence band 00, it is at a longer wavelength in comparison to the 00 absorption band. And it is happened due to the deformation of the excited state, electronic state. And as a result, the Morse potential energy curve of the excited electronic state is shifted to the right side. This is the potential energy. This is the first, and this is the second, and this is the ground state Morse, not exactly drawn here. This is the ground state Morse potential energy curve, and this is the excited state Morse potential energy curve. There is a long shifting. If these types of shifting occurs to the excited state, and actually then there is a shifting of this 00 band. And actually these types of shifting of this excited electronic state, it occurs mainly, there are different regions, aggregation, molecular aggregation, molecular structural deformation, and also several other things. As a result, this excited state shifting occurs. Impurity presence in the sample, it also leads to the shifting of this excited electronic state. Okay. And this deformation of the excited state happened due to the same following reasons. In most of the cases, due to higher concentration or molecular close pack association or charge transfer types of interaction, or due to pH dependent deformation of molecular structure, this excited state is deformed, and as a result, 00 band of absorption and fluorescence, they do not coincide. One band system lies in the visible or near IR, the other band system lies in the visible to UV or near UV region. And also here, you see, this is also, you see that one of the absorption spectrum. You may also find these types of absorption spectrum. And here, in this absorption spectrum, you see there are distinctly two different types of band system. This is one, this is the longer wavelength band system, and this is the shorter wavelength band system. In several samples, several solid thin films, and also several other things, you may find these types of absorption spectrum. And here you see this, the shorter wavelength or high energy peak or spectrum, it consists, due to the transition from the GS to ES1, and this is your ES2. And generally it occurs from transition from GS to ES2. And this longer wavelength transition, it occurs from GS to ES1 transition. That is the ground state electronic state to first excited electronic state transition, this longer wavelength band system occurs. And when there is transition from ground electronic state to second excited electronic state, then this shorter wavelength absorption spectrum occurs, but its intensity is generally very, very small. In many cases, most of the cases, you may not find it. You may find only one type of band system. And in this one type of band system, there are several vibrational peaks, of course. And here also, the intensity is very small. But in some cases, you may find it also. And these two band systems in the absorption spectrum come from ground state to the second and first excited state respectively. But one thing you must mention, it must be noted that you may find these two types of band systems in this absorption spectrum, but in fluorescence spectrum, you find only one type of band system. If you find two different types of band system, then this occurs due to presence of impurity. You must note this thing. And now, in dilute solution, these two band systems are observed. However, with increasing concentration or ratio in the solid state, shorter wavelength band system decrease in intensity and sometimes vanishes. And it's a comparison of this absorption and emission processes. And also there is also quantum yield, that is the number of photons emitted and number of photons absorbed. And quantum yield, measurement of quantum yield, also some particular samples, this is also in comparison to some standard samples. This is important. And following are the important regions for the scope of quenching. Energy may be lost due to vibrational transition, collision with the solvent molecules, heat transfer, but only a part of the light absorbed is emitted. Only a part of the light absorbed that is emitted. And it is because of this that the quantum yield in most practical cases is not equal to 1. And quenching of process may also occur due to the presence of some foreign molecules or impurities in the solution which act as a quencher. Quenching may also occur due to some structural rearrangement of the molecules which drives the fluorophore to a conformation that reduces the process intensity. In case of process resonance energy transfer, also process of some samples may decrease. Now, this is the experimental setup of a fluorescence spectrophotometer, and here you see that this is a monochromator, that is excitation monochromator. First of all, this is a light source, and you have to change this excitation monochromator, and at a fixed position you have to keep fixed. You have to keep it fixed at a particular position so that a particular wavelength or frequency EMR radiation, it is incident of the sample. You cannot change this monochromator to change the frequency during the fluorescence experiment. You have to give only one frequency, light. And then you have to take, this is a emission monochromator, that is, you have to consider it in a 90-degree geometry, but not in a direct. In case of this absorption spectrophotometer, you see that we measure, we just keep it, the detector here, in a 180-degree geometry, and this angle is a 180-degree angle. But in case of fluorescence spectrophotometer, fluorescence spectroscopy, we take it a 180-degree geometry. And because you see that if you want to take the place the process emission monochromator here, then what happens is that the direct light may also enter. Direct light, of course, enter, and you won't get any fluorescence emission. You have to avoid the direct light, you have to take it in the 90-degree geometry. That is, you have to place the emission monochromator in the 90-degree arrangement with respect to the direction of this incident radiation. Okay, and therefore, and then this emission monochromator, it is gradually changed to collect to find the different emission of different wavelength, and corresponding intensity. You have to record it here. And this light source may consist of both UV and visible source, both, and there are two monochromators, that is the grating. The first monochromator is called the excitation monochromator, excitation grating. You see, this is the excitation monochromator. It must be kept fixed at a particular, to allow only a particular wavelength incident electromagnetic radiation. It is used for selecting the particular excitation wavelength of the EMR. The excitation wavelength is kept fixed throughout the process of taking the fluorescence spectrum. And when this particular wavelength of EMR is incident on the sample, maybe liquid, solid, or film, then the molecules absorb radiation and go to the excited state. Now, fluorescence emission occurs when the molecular transition takes place from the excited singlet to ground state singlet. The emitted fluorescence radiation is collected by the emission monochromator placed at 90-degree geometry arrangement with the sample container, as shown in this figure. And this 90-degree geometry arrangement is necessary for avoiding the entering of direct light to the emission monochromator. Emission monochromator is scanned slowly to desired wavelength range for recording the fluorescence spectrum. And while the excitation monochromator is kept fixed at a particular wavelength to allow only the fixed excitation wavelength of the image. And in this way, and therefore you see that it is gradually changed to collect to scan all the wavelength and corresponding, you have to record the corresponding intensity. And in this way, we record the fluorescence spectrum. And these are the basic principles of this UV Vis absorption and fluorescence spectroscopy. And also there are other, for research purpose, you have to use some other, you have to study some more. Okay, and there are some questions also. Okay, and then thank you, I should say.
Thank you, sir, for a very informative talk. Now, if participants have any questions, you can put it on chat box. Sir, there is one questions from Dr. Jasim Uddin. Should I read for you? Or
yes.
Sir, basic introduction to the principle and working of UV Vis absorption spectroscopy, fluorescence spectroscopy, and Brewster angle microscopy. I very much benefited from an.
Okay, thank you. Okay, actually, these are some basic introduction, and if you want to do research or others, then you have to study something more. Actually, these types of fluorescence, UV Vis absorption and fluorescence spectroscopy, these are used this is the basic instruments for material science research, and these are used in pharmaceutical industry, these are used in chemical industry, in physics lab, in chemistry lab, in biological labs, even in electronics lab, mechanical lab, civil engineering lab, and others. Okay, and thank you then. May I stop now? Okay, thank you.
I think there is no other questions. So let's move to the online MCQ test based on this 6 session that we completed. For the test, a Google Form link has been sent on WhatsApp group as well as Google Meet chat box. So with this, I end this 6 days ATAL FDP on behalf of Department of Physics, Tripura University. And from Monday, hands-on session will be start. Thank you, everyone, for your presence. Good night.
Thank you. Good night. Thank you, sir. Thank you.
And exam link will be remain open for 15 minutes. So try to do it first.